right, let's look at wavelength, frequency, and energy. We can't talk about electrons until we have a good understanding of the type of energy that they can exist with. So the wavelength, which is given the Greek symbol lambda, is going to be the distance between two peaks of a wave. And typically the wavelength is measured in nanometers. Over here on this diagram, you can see that the wavelength is the distance between two peaks. So here I have a peak here and a peak here. So that's going to be the distance of my wavelength. I just want to be very clear about this. Although that is the general definition, you can pick any two identical points on a wavelength, and the distance between those are going to be a wavelength. So if I go from the valley to valley, that's also going to be the distance of the wavelength. Or if I wanted to go here to here, that's also the distance of the wavelength. But generally, we just talk about it in terms of peak to peak. Now, the frequency, which is given the Greek symbol nu, which kind of looks like a cross between a V and a U. Here's the symbol of lambda and nu down here as well. It is the number of times the wave peak passes a point in space. And what's important about this is it's over a specific period of time. So this is usually, the frequency is usually measured in what are called hertz. And hertz are given the symbol Hz. Now, 1 hertz is equal to an inverse second. Now, inverse second just means per second. So a frequency is going to be a count how many wavelengths there are per second. Now, the speed of light, how quickly light moves, is equal to 3 times 10 to the 8 meters per second. So we can make a relationship between the speed of light and the wavelength and frequency of light. And that is c, the speed of light, is equal to the wavelength times the frequency. So let's look at an example of how we can use that equation. The detection of lead from a gunshot residue is accomplished by measuring emitted light that corresponds to a wavelength of 220.4 nanometers. So this is going to be my wavelength. What is the frequency of this wavelength of light? Now, I want to solve for the frequency, and I know from the previous slide that the speed of light is 3 times 10 to the 8 meters per second. So one of the first things I notice is I can use the equation C is equal to lambda times V, or lambda times nu. If I rearrange this to solve for nu, I'm going to get nu is equal to C over lambda. Now, one of the things I notice next is my lambda is in nanometers and my speed of light is in meters. Those are not going to cancel each other out when we put them in our equation. So I have to convert wavelength into meters before I can calculate this. So to do that, I'm just going to use the prefix for nano, which is times 10 to the negative 9. And I can do 1 times 10 to the negative 9 meters per 1 nanometer. Notice that my nanometers cancel out, and I'm going to be left with units of meters. So since that's just multiplied by 1, I can just add the times 10 to the negative 9 to the end of my number, and we will be in units of meters. So let's plug in our numbers. We have 3 times 10 to the 8 meters per second. This will be a value that will always be provided for you on your quizzes. And we can divide that by our lambda and make sure it is in meters. So it's going to be 220.4 times 10 to the negative 9. So notice my meters cancel out, and I'm going to be left with units of inverse seconds or per second. Now, when we calculate this using our calculator, it will equal 1.36 times 10 to the 15 hertz. Remember, 1 hertz is equal to an inverse second, or 1 over seconds. I think the hardest part about this type of problem is recognizing that you have to know how to use your calculator in order to do this problem. So if you need help or you're not getting this answer, please send me an email. I can try to talk to you about using your calculator over an email. You can come see me in my office, or we can set up a Zoom meeting. Now, as the frequency of the light increases, so does the energy. So if I have a shorter wavelength, meaning my frequency is increasing, then my energy is also going to increase. So we have these equations down here. Energy is equal to H times nu. H is a Planck's constant, equal to 6.626 times 10 to the negative 34 joules times seconds. Joules is a unit of energy. So whenever we're calculating energy, most of the time in chemistry, it is going to be in units of joules. So let's look at an example where we can use these different equations. Over here, I have provided all of the constants in different equations. We have E is equal to H times nu. C is equal to lambda times nu. So if we solve for nu and then plug that in up here, we get E is equal to HC over lambda. So a black light is used in crime scene investigations to expose evidence not visible under normal lighting or the naked eye. Black light has a wavelength of 365 nanometers. What is the frequency of the wavelength? So I have my wavelength, and I want to solve for the frequency. So I'm going to look at my list of equations and find out which ones have both wavelength and frequency and don't have any other variables. And I can use this equation right here, similar to what we just did in the previous problem. So my nu is going to be equal to C over lambda. So I can plug in my C, 3.00 times 10 to the 8 meters per second. And I can divide that by my wavelength. Now remember, your wavelength must be in meters. So I can do 365 times 10 to the negative 9. Remember, nano means times 10 to the negative 9 meters. So we can put this into our calculator. Go ahead and get your calculators out. We can enter 3 times 10 to the 8 divided by 365 times 10 to the negative 9. Now, when you are entering this into your calculator, you don't ever want to press the multiplication times button or type in 10. You always want to use your calculator's exponent function. So for this, we get 8.22 times 10 to the 14. And since we canceled our units of meters, I'm going to be left with units of inverse seconds. So we have hertz. And that is good because I'm trying to solve for frequency, and that is a unit of frequency. Now we can also use all of this data to calculate the energy of the black light. So E is equal to H nu. And I just calculated nu. So this is perfect. H is a constant, 6.626 times 10 to the negative 34 joules times seconds. And I can multiply that by the number that I just calculated. 8.22 times 10 to the 14, remember hertz, is 1 over seconds. So notice what happens to my units of seconds. They cancel out, and I'm left with units of joules, which is good because it's asking for energy. So if we plug this into our calculators, we have 6.626 times 10 to the negative 34 times 8.22 times 10 to the 14. All right, go ahead and put that in your calculator. What do you all get? Yep, that is what I get as well. 5.45 times 10 to the negative 19 joules.